Hey, just a quick note before the video starts here. This is all made for the exclusive purposes of education, commentary, and criticism under fair use, and all footage used from the film Star Wars A New Hope belongs to Disney and Disney alone. So, please don't copyright strike me. Thanks, and now back to the video here. Everyone knows about Star Wars, right? A band of plucky rebels struggle to take down the evil Empire, who is in the process of building a massive moon-sized planet-destroying superweapon, which ends up getting blown to bits during a staring starfighter battle. Spoilers, I guess. But come on. If you haven't seen Star Wars yet, something is seriously wrong. Anyways, while most people are more invested in the action or plot, the entire time I was watching A New Hope, I couldn't stop thinking about one thing. How in the heck does that Death Star stay in orbit? So, I mean, come on. That thing's massive, and it has got to weigh a ton. And while everyone else would simply shrug this off, this is probably different, so it just works. That wasn't a good enough answer for me. So, I decided to see the physics behind the Death Star, and see if it would actually be able to sustain orbit, or if it would just kind of fling itself into deep space, like a giant extraterrestrial slingshot. So, this is the physics of the Death Star. But before we can start worrying about giant space stations, we need to learn a little bit about what gravity is. Gravity is the force that attracts two objects to each other. For example, gravity pulls us back down to Earth when we jump. Without gravity, we would simply fly into space whenever we jumped off the ground. On Earth, gravity works pretty simply. To find the gravitational force on an object, you multiply its mass by the gravitational acceleration, which happens to be 9.8 meters per second on Earth. And boom! You have the force of gravity acting on that object. However, while this works well for something on Earth, it doesn't quite work as well for finding the massive giant things in space. And since things in space are so massive and so far away from each other, there's got to be another way to find the gravity between these things. And this is where our good friend Isaac Newton comes in and saves the day. Meet Newton's law of gravitation. To get the gravitational force between any two objects in space, you multiply the product of their two masses by the universal gravitational constant, which is about 6.67 times 10 to the negative 11th, or this super small number, and divide it all by the square of the radiuses between the two objects. And boom! Gravity! This will be a major help in figuring out gravitational forces, especially when finding the gravitational force on the Death Star. But back to Star Wars, there were several problems that I encountered in finding the gravity of the Death Star. The first one was that a lot of the information required, mainly masses and orbital velocities, doesn't exist on the internet. Thus, I was forced to improvise and find/create them myself. I scrounged what I could off of the official Star Wars wiki, Wikipedia, including a lot of the data about Yavin and Yavin 4, but I encountered a significant roadblock when finding a lot of the information for the Death Star. Wikipedia said that the Death Star was made out of a material called quadanium steel, which isn't a real metal. But being the nerd that I wasn't going to let that stop me. I dove headfirst into the internet to figure out what this mysterious metal was made of, only armed with the knowledge that it was a high-strength steel alloy. After digging through the catalogs of countless metal manufacturers and introductory mechanical engineering lectures, I was able to figure out that quadanium steel is a tungsten-based tool steel alloy with an extremely high tungsten concentration, making it very durable, heat-resistant, and extremely strong. Strong enough to work in space. And using that, I was able to figure out a rough concentration for our quadanium steel, and using some math, I was able to figure out that the density of this fictitious material turned out to be 9.34355 grams per cubic centimeter. Then, guess, assuming that the metal is about 15% of the station's mass, I calculated the density of the whole Death Star to be a whopping 0.0014 grams per cubic centimeter. Then, plugging into everyone's favorite equation, the DMV, density equals mass over volume, I calculated the mass of the Death Star to be about 2,267,978,568,990,000 kilograms. Another problem that I ran into during my calculations was the fact that there was no canonically confirmed orbital radius for the Death Star. Thus, I went with the tried and true method of pixel measurements. Using an image from the Death Star, I was able to find out the fact that the orbiting radius of the Death Star was a shockingly low 128,930.8176 kilometers, which, given the fact that the radius of Yavin itself is only 100,000 kilometers, this would technically be within Yavin's atmosphere. But, ignoring that, I was able to figure out the fact that the Death Star would have to travel 105,537.5 kilometers of linear distance in the 15 minutes that it would need to enter the firing range, and then using that information I was able to calculate the velocity of 117,263.9 meters per second, and then its centripetal acceleration, which could be used to find the net force. And from here it was just a simple force problem. Knowing the fact that the only force acting on the Death Star was the force of gravity from Yavin, I set that equal to the net force, which, through Newton's second law, is equal to mass times acceleration. From there, I was able to plug in the Death Star's mass and its centripetal acceleration to figure out that the force of gravity required to keep the Death Star in orbit was 2.5103 times 10 to the 17th newtons. And then, I used Newton's universal law of gravitation to find out how much gravity it actually had exerted on it, which was, drum roll please, 3,428,283,459 newtons, which is significantly less than what was needed. Initially, I was satisfied with this conclusion. I thought, well, I figured out that the Death Star would slingshot itself into space. It doesn't have enough gravity to hold itself in orbit. And then I remembered something. The Death Star isn't the only thing in this situation that's moving. Chasing after Yavin 4, right? So, it would have to catch up to Yavin 4, which is also moving, meaning that it would have to cover a significantly larger amount of distance in the same time, meaning that its velocity would actually be different, causing its required gravity to be different. So thus, I went back and started redoing a lot of my calculations to fit with this updated circumstances. First, I had to find a lot of the values for Yavin 4, and I started doing this by going back to our still image and doing some more pixel measurements. I was able to figure out its radius, which was about 139,500 kilometers. And then using this, I was able to figure out its actual gravitational force of 3.95 times 10 to the 18th newtons. And then I went back and sort of reverse engineered the velocity by finding its centripetal acceleration and then using that to find the velocity of the massive planet, which ended up being only 13.419 meters per second. And then using this, I found its angular velocity, and then I used that to find the additional angle in relation to Yavin that Yavin 4 would end up traveling during said 15 minutes. And I found that to be a whopping 8.65 times 10 to the negative 5th degrees. With this new information, I updated the angle that the Death Star would have to travel in 15 minutes, with it now being 46.900865 degrees, and then updated the distance that it would travel, basically adding an additional 200 meters. And then using that, I recalculated the velocity and the centripetal acceleration, with its new velocity being about 117,264 meters per second, and its new centripetal acceleration being 106.653 meters per second squared. And from here, I just recalculated the force that I had calculated earlier, using the new centripetal acceleration of 106.653 meters per second squared, and I found the new required gravitational force to be 2.4189 times 10 to the 17th newtons. Still significantly higher than the gravity that Yavin is exerting on the Death Star. And then here, just for curiosity, I wanted to see how fast would the Death Star have to actually go in order for it to maintain its orbit. So what I did is I plugged in the actual gravity that it had exerted on it as the net force, and then used that in Newton's second law equation to solve for the actual acceleration, which ended up being 1.5116 times 10 to the negative 6 meters per second squared. And then I used that to find the actual linear velocity that it would have, and that came out to be a whopping 13.9603 meters per second. At this point, out of curiosity, I wanted to see just how long of a window the Rebels had until the Death Star was in firing range, if it was traveling at the velocity that it would have to be going in order to maintain its orbit. So what I did is I took the Death Star's position and added the maximum distance that the Death Star could be away from Yavin 4 and still be within firing range, and set that equal to Yavin 4's position. And after I solved all that out, I ended up figuring out that the Rebels had approximately 6.182 years to destroy the Death Star. I mean, they could literally attack once, fail, sit and ponder it for 5 years while they figure out how to do it better, go back, try again, and still have a year to spare. So, what have we learned here? Well, for one, we know that the Empire is really, really bad at physics, because their massive planet-destroying superweapon was going way, way, way too fast and required significant amounts of gravitational force that it just didn't have, and thus would be slingshotted into the far reaches of space instead of turning around and firing at the planet. And two, even if they were going at the velocity that they needed to be in order to maintain orbit, that would in turn give the Rebels literally years to plan out how they're going to destroy the Death Star. So, long story short, don't build massive planet-destroying weapons, and if you're going to, make sure you put them at the correct orbit and velocity, because otherwise they're just kind of pointless and they're going to be flung into space instead of blowing up said planet that you really, really, really wanted to blow up. So, be sure to smash that like button with 2.5103 times 10 to the 17th newtons of force to ensure that more people are made aware of the physics of the Death Star.